MPI plus hStreams in NEMO5 Partitioning Xeon Phi. I'm a PhD student from Purdue ECE department, and I'll give this presentation. So first, it's an overview of NEMO5. What is NEMO5? It is a multi-scale semiconductor device simulation software from ab initio to TCAD for realistic devices. We don't do ab initio simulations, but we map the parameters from ab initio into type bending mode and then simulate all the way up to devices like transistors, LEDs, which was typically done in TCAD softwares. And we are also multi-physics and multi-purpose. Some 3 examples, topology insulators, quantum computing, and nanowires, and many, many more, like LEDs. So we are used by more than 400 academic and industrial groups. The reason I'm mentioning Intel here is quite interesting that Intel TCAD and new devices groups use our software to design one single transistor. You will see 7 nanometers or even smaller ones. And we are also funded by IPCC to do this development. So we're to very end of the business line of Intel. Yeah. So we have roughly 500,000 lines of code by 65 authors over past 7 years. Right now, we have a large group, 1 professor, 3 faculties, 1 scientist, 2 postdocs, and we have 25 students. And it's really hard to get fundings for students to directly work on HPC, but we managed to have 3 or 4 of them. So now comes to the approach. Since we have 25 students, most of them are physicists, electronic engineers. They take the science-oriented approach. So they use gradual effort to have good performance, not the best, because they are not HPC-oriented. But for me, I'm an HPC-oriented student. We try to maximize the performance of our software infrastructure, which is shared by all the simulation modules. Oops. No. So yeah, here talks about what we did with KNC. I mean, we are ongoing work to compile for KNL, but here I just talk our work with KNC. So we tried native mode. It doesn't have the binary compatibilities. It's a pain because we depend on more than 15 third-party libraries. We tried automatic offloading, but it doesn't have fine controls, and it needs large matrices. So we took 2 approaches. One is compiler-assisted offloading. That is used for 2 MPI process per node case. And we use hStreams. That's more flexible for more than 2 MPI processes per node case. A good point I like that hStreams mix and match of simplified APIs for easiness and core APIs for fine controls. They can work together. So here is the compiler-assisted molding. We did this in collaboration with Intel Parallel Computing Lab from 2013 to 2015. So it basically distributes the workload between host CPU and Xeon Phi. Here is an example of the cluster we have at Purdue. It's 16 cores CPU plus 2 KNCs. So this is problem independent because it distributes a large matrix, and whenever there's a matrix multiplication, it's not dependent on the problem you are going to solve. So here's the approach with hStream. This is problem dependent because when we have multiple MPI process per node, say for small 1D or 2D simulations with relatively small matrices, we can use hStreams to store the intermediate result on mic. So this is problem dependent, and this is used by our science-oriented students. So each MPI process has a virtual Xeon Phi in smaller size. We think that smaller number of threads can benefit the efficiency for smaller matrices. So here's an illustration, 8 MPI processes per node. So 2 cores are used by 1 MPI process, and the 60 threads are used by 1 MPI process. So here's a brief introduction, say how we do this. We get the local communicator with MPI comp split, and then get the local rank and the comp size, then calculate the number of threads for one MPI process. So this example, 4 MPI ranks shares one mic, so 60 threads per rank. And then this is how we do this. hStreams provide a variable of CPU mask. It's 240 bits, so each MPI process just need to set the corresponding bits with macros provided by hStreams. Sorry, it's changing automatically. So here the 4 ranks case. Then supply this CPU mask to the hStream at log domain to set the thread affinity. So it's easy to do. Then here's some microkernel benchmark. We do quantum transport. There are 2 types of major calculations we did. One have 3 multiplications, the other have 5. So we use square n by n dense matrices for benchmark. And actually, the speed up is calculated by Xeon Phi only with versus CPU only. Of course, it's not the optimum, but we just want to show how easy you can get the speed up. So we can see that we got somehow good speed up for matrices larger than 500 by 500. The reason I mentioned that this is problem dependent is that we can store the intermediate result on mics. We don't need to move it back to a host as what we did in the compiler assisted mode because it's just used for 1 multiplications. So yeah, for the conclusions, we feel that it's good to have a mixed team internally. Of course, we appreciate the help from Intel and all the supporting staff from the computing sites we use, because internally, students with HPC orientation and the science orientations can really sit in the same office space and discuss what they need and what they are going to do. And some major thoughts for the science-oriented students, they really want libraries rather than pragma directives, because libraries is easier to understand. It's function cost, just like what they learn from the programming 101. And they like good plug-and-play performance with gradual effort because they need motivations. They are science students. They are funded to do science rather than speed up the code. And they cannot graduate by writing a code that can run 3 or 5 times faster. So they need motivations. But for me, I'm a HPC-oriented student. I don't have restrictions. I need to do research. I need to use all the possible ways to speed up our code. But I just have one suggestion, like we need to find controls over those libraries. Just I mentioned for hStreams, it's a mix and match of easy to use interface and more fine controls later on that I can help the science-oriented students. And finally, a remark that the balance between man hours and the performance improvement, yeah, we have limited number of students, actually students focusing on HPC. So yeah, we really need to balance this, and we really want to encourage the science-oriented students to write the good simulation modules. Then we don't need to spend a lot of time to somehow rewrite their modules. Yeah, finally, we acknowledge the funding support from IPCC and the cluster support from Purdue Computing Center. Thank you. Just I'm the second-year PhD student. Yeah. Yeah, but somehow I'm just working, kind of, I wouldn't say leading the HPC effort in our group, but somehow in this way. Yeah, my boss really focused on the science side. Yeah. 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 Thank you.